In this video, we look at a quantum harmonic oscillator, which is a model for describing vibrations in molecules. Take a diatomic molecule with two atoms, with masses m1 and m2, connected by a chemical bond which we model as a spring, with a spring constant of K and a length of L0 plus x, where L0 is the equilibrium length of the bond and x is displacement of the bond length from that equilibrium length. Recall that the oscillator frequency for such a system is omega equals to the square root of k over mu, with a reduced mass mu equal to m1 times m2 divided by m1 plus m2. The potential energy function for this harmonic oscillator is a function of the displacement x. V of x equals to 1/2 kx squared. Here's the time-independent Schrödinger equation for this system. Minus h bar squared over 2 mu d squared dx squared operating on psi plus 1/2 kx squared. This is the potential energy times psi equals E times psi. In order to solve this equation for psi, we need several steps. In the first step, we do some substitutions. The main goal is to simplify the expressions. We introduce a scaled energy epsilon, which is equal to E divided by h bar omega over 2, and we introduce a scaled displacement z, which is equal to x times the square root of mu omega divided by h bar. Both epsilon and z are dimensionless. With these substitutions and a little bit of work, the differential equation reduces to d squared dz squared of psi plus epsilon minus z squared times psi equals 0. Now this looks definitely simpler than before. Second step. Let's examine the last equation in the limit of very large or very negative displacement z. Then epsilon can be neglected compared to z squared, so that the differential equation simplifies to d squared dz squared psi minus z squared times psi equals 0. The general solution for this equation contains two exponentials. Psi of z equals some constant a times e to the negative z squared over 2 plus b times e to the positive z squared over 2. You can check this solution by substituting it back into the differential equation. Mathematically, this is all correct, but the second term grows without limit with increasing z and would make psi not normalizable, so we have to drop it. The first term, on the other hand, is a quadratically decaying exponential that's also called a Gaussian function. It goes to 0 as the magnitude of z increases, and therefore it is normalizable. This is the form psi approaches to in the asymptotic limit of large z. Third step. Let's go back to the original equation. We can now make a better guess or ansatz for the overall solution of the Schrödinger equation by peeling off the asymptotic behavior we found. Our ansatz is going to be psi of z equals h of z times e to the negative z squared over 2. hz is a yet undetermined function. It is a great unknown. We have to find out. Substituting this form of psi z into the Schrödinger equation gives d squared h over dz squared minus 2z times th dz plus epsilon minus 1 h, and all that times e to the negative z squared over 2 equals 0. Now, since the exponential term cannot be 0, the first term in the square brackets has to be 0. So now we have a differential equation for hc, the great unknown, and we have to deal with that. Now comes the fourth step. Since we don't know anything about h at this point, let's use a general power series expansion for it. h of z equals the sum over m equals 0 to infinity of am z to the power of m. This is a general polynomial in z, where am are the polynomial coefficients. M is the integer exponent that runs from 0 to infinity. Let's insert this expansion into the differential equation. After a bit of work, we get the sum over m equals 0 to infinity of m plus 1 times m plus 2 times a m plus 2 plus epsilon minus 2m minus 1 times am, all in square brackets, times z to the power of m equals to 0. This is another polynomial in z, with a coefficient in the parentheses. For this polynomial to be 0 as required by the equation, each coefficient in this polynomial has to be 0. Rearranging this gives a m plus 2 equals epsilon minus 2m minus 1 divided by m plus 1 times m plus 2, the whole thing times am. This is a recursion formula for the polynomial coefficients. For example, if we start with a value for a0, this equation gives us a value for a2, which then gives us a value for a4, and so on. If we start with a value of a1, we get a3, and then we get a5, and so on. Clearly, there are going to be coefficients for arbitrary large m, both even and odd. This, however, means that the polynomial blows up, which would make it unnormalizable, and therefore unphysical. A careful analysis shows that the only way these polynomials are not going to shoot up to infinity for large c is if the series of coefficients terminates. That means there must be a maximum m, let's call it n, above, for which all coefficients am are 0. In other words, there must be an n where this here equals 0. Let's write it out. Epsilon minus 2n minus 1 divided by n plus 1 times n plus 2 equals 0. N could be any integer, 0, 1, 2, and so on. This expression can only be 0 if the numerator is 0, which leads us to epsilon equals 2n plus 1. Combining this with the definition of epsilon, which remember it's a scaled energy, finally yields E equals h bar omega times n plus 1/2, where omega is the square root of k over mu, and n is 0, 1, 2, and so on. These are the quantized energies of the stationary states of the harmonic oscillator. N is the associated quantum number. It starts at 0 and is any positive integer. Let's add a subscript n to the energy to indicate this quantum number. If you look back, we see that the energy quantization results from our requirement that the wave function is normalizable and doesn't blow up with increasing z. That danger existed twice. First, we had to throw out one of the exponentials in the asymptotic solution. And then we had to require that the polynomial terminates. That was this equation here. In conclusion, we've derived the quantized energies of the stationary states of the harmonic oscillator.